Okay, so now we can get back to kind of where we left off last time with the hysteresis of thresholding techniques so that you can find these canalically. And so we sort of saw how that worked for one slice. And where we see that sort of more usefully is when we look at sort of an entire image of what this allows us to get out of it. And so the circles that you see, or sort of the spheres that you see, are the individual cells that we had in the image, and these green structures are then the canaliculi that are connecting them together. And by using this hysteresis threshold technique, we're able to identify these links between cells, which then allows us to generate sort of the network that we have for the cells, which I think is shown. Nope. I think you can see it barely here, where you then have these red lines that show you which cells are connected together and which ones are not. And this then lets you study how signals might propagate through this network because you've sort of identified the topology, which from the cells themselves you wouldn't have had. But once you can find out where these canaliculi, these little channels are, then you can start to identify that these cells are connected together. And this is just a small segment of the image. And so what this image actually has is, I think, around 60,000 of these cells. And so having the network that connects them all together gives you a huge amount of information that you can then study to see how the bone responds to different stresses and what aspects are important and which ones are not. So now kind of moving on to more complicated images. And so we've briefly talked about this before, where we had this idea of, the image doesn't just have to have one value. It can have many values, as we called sort of depth before, at each point. And so this case shows an image where you have a intensity, a rotation, a shape. I think that's it, at each position. And so you have many more channels of information at each point that you can use to analyze it. And so if you look at things, digital cameras produce at least 3 channels of color. MRI images can produce dozens of different channels at each position that describes a different sort of physical property of that point. Raman shift imaging produces an entire spectrum. Infrared imaging also does the same thing. And so this is used, Raman shift imaging, for sort of chemical identification, often in biological samples. The infrared imaging is used, I think, for the latest sort of missile targeting systems. They have a hyperspectral camera inside of them so that they can see not only the colors in the image, but also heat and other infrared pieces of information, which make it much easier, evidently, to target something. And coherent diffraction techniques can produce 2- or 3-dimensional entire diffraction patterns at each point. And so that's where, this is already a very compressed representation of what you could get out of a 2- or 3-dimensional diffraction pattern at each point. And so one of the other things we can do to images is this idea of feature vectors. And so that we have the intensity, which is what we normally measure at each point, and that's sort of what we show in this image. But there's a possibility to have a lot more information here. And so, each position here is x and y, and this value is intensity. And that rather than thinking of this as different depth channels, we can describe each point or each value there as a feature vector. And so that there's an entire space of different values that can go onto it, and this would then be sort of a length 1 feature vector, but you could extend beyond this. And so if we look at why feature vectors are important, if we go back to this very simple ring example, where we have sort of this ring that we're trying to identify, and if we apply a simple threshold, then we get the ring, but we also get this point in the center and this point at the edges. And so using a simple threshold is going to be very difficult. If we add a new feature to this image, and so one of the features that we could add would be distance from the center. So here, center of the image is there, and that color represents the distance from the center, which is an idea, again, we'll come back to later, but right now just accept that this is kind of a feature that you can add to it. Now at each position we have x, y. We also have the distance from the 0, 0 point. And so now when we look at sort of the results, we can plot these two components against each other. We see intensity on the x-axis and distance on the y-axis. And we can see kind of where the values fall. And with what we see kind of clearly here is that the intensity gives us one piece of information, but we also end up with these points and these points. And if we include distance and intensity to select this, then we can do a much more exact job of finding this ring that we're trying to identify. And so yeah, when we see here, if you sort of take density and threshold together and you draw that box around it, that you can get a much clearer result from your image than we had before. You can sort of also apply this idea of ground truth and ROC curves to it, where you have the ground truth, you have the ROC curves, and rather than just having one feature that you're looking at, you can look at sort of your entire feature space. And so with this, this just shows one of the features or one of the superpositions of the features, but then you can quantify it with these curves, just like we had before. And you can optimize which combination of these features or which representation of this feature gives you the best result. Because of course, once you get a more complicated space there, it's difficult to identify sort of what you do with all this information. And having this ROC curve provides you that sort of metric that you can try to optimize. And so particularly when we start thinking about sort of what do machine learning techniques do and where do deep learning approaches become useful for image analysis, it's always critical that you have some single metric that you're trying to improve. That, you know, making your image better isn't something in itself that you can quantify. You need to say, we're trying to maximize the area under this ROC curve, and we adjust these parameters, or we look in this general space, but that's our goal. Because if you don't have a goal, then there's no way an optimization algorithm can work towards it. And so even with these examples with Go and chess and those other games, the goal or the concrete measure that they had is the scoring of the board. And so their tool had an ability to look at a board and say who has an advantage at this point. And their algorithm then chose moves to optimize this advantage that the computer had. And so it looked at all the possible moves, or sort of the options for moves it had. It evaluated the score at each one of them, and it says this is the best move because this is where my score or my advantage is the greatest. And so those are always sort of the ideas that you want to keep in the back of your head when you're doing these approaches, is that you want to have some clear metric that you're trying to optimize. Because once you've defined this well, then you can let other tools search the parameter space or optimize the combination of filters and thresholding and morphological operations. The really important part is that you know when you're successful. You know, so that when your curve looks like two straight lines that go to this point, that it's perfect. And so once you can sort of define that, it's much easier, or it's very easy to figure out which components you can automate or optimize or replace. But if you don't have this definition well, then it's going to be very challenging to do that. And so yeah, we have the curve in the other direction as well. And this is where you can see sort of the random guess. What we can see is sort of common features. And these are just three brief examples that we have. Is that you have sort of your intensity image here. And you can use a Gaussian filter as actually a feature. And so in the second lecture, you covered Gaussian filters to sort of filter out noise in your image, but you can also use it to provide different kinds of information in your image. And so can you think of why a Gaussian filter might be useful?
It's giving you a summary of local information. It's taking a whole neighborhood and summing it up as a single value.
Yeah.
For each box.
Right. So that's exactly what it does. So when you have this Gaussian, it sort of smooths out the area around the point that you have and gives you information on that. And so when you're trying to say this is part of a ring because it has a bright intensity and all of its neighbors have bright intensities as well, that having the Gaussian as one of your features lets you show that. Because the Gaussian will sort of be high and constant when you're in the middle, and if you're very close to the edge, then the difference between your Gaussian and your current value can be very high. Similarly, Sobel, which is one of these features that we've talked about before, that sort of enhances the edges in your images, we can include as a feature vector. And so we don't use this by itself, but we use it as another piece of information to help us identify what's inside the image. And so any idea of what Sobel would be helpful for? Or what sort of tasks it would be useful to look at? Yeah. And when might that be helpful?
For example, the image you showed in the beginning
Uh-huh.
where the borders get smeared up with the background.
Yeah. So you can use it on images like that where your edges aren't very strong. And then you can combine the Sobel with other pieces of information like the Gaussian and like the intensity to try to find the boundaries of regions much more accurately. And that by having two pieces of information rather than just one, you can sort of identify if it's noise or not. That by looking at sort of the Sobel and the intensity, you can say, okay, the value's high and it's Sobel, and so it's the edge, but we're on the inside of the object rather than the outside of the object. And so it just gives you much more information to work with and makes your thresholding process much easier. And so these are just two example features. In reality, there's hundreds of features you can generate at each point that describe sort of that image or the texture or the different values you have very well. And so these tools we see sort of constantly being used to identify and understand images better because the intensity by itself doesn't give you that much information. And so if you try to segment just based on the intensity, it can be very challenging to find the features you want in an image. So yeah, so when we look at the feature vector that we have here, you can sort of plot the features against each other and you can see what information they show. And then you can see sort of, you can combine it with knowledge about the sample. And so in this case, we know this is part of the ring and this is part of the background. And then we can see what features differentiate this well for us. And so if we had distance here, that would of course be another factor that would be very strongly differentiating. But yeah, when we have intensity, Sobel, and Gaussian, we see that sort of Sobel doesn't tell us much about what's in the ring and what's in the background, or rather little, but the Gaussian and the intensity both tell us some information about that. You can also make sort of these cross plots, which we won't really do much of in this class, but they're important to have seen before. And this is where you have a scatter plot that shows you all of the different variables or components of your feature vector against all of the other components. And so along this x-axis, we have intensity, Sobel, Gaussian, and intensity, Sobel, Gaussian. And so this is intensity versus intensity, which is why nothing's plotted there. And this is then intensity versus Sobel. And so you can see the relationships between these different vectors. And so what we see here is that intensity Gaussian is more or less a line, which means that they're very well correlated, and we're not getting a lot of information from the Gaussian, and so it doesn't make sense to really use that as a feature vector. Or we should use intensity or Gaussian, but using both doesn't give us more information. What we see with the Sobel is that it provides, we want this to be as kind of random as possible, because that means it's providing different information. And these colors then represent this structure that we've identified before. And so this In sort of contrast to the ROC method, this gives us more insight about how we can combine these features together and which features are useful and which ones are not. The ROC just gives us sort of a summary over the entire image, and this gives us a better understanding of which components are telling us about what kind of information in the image. So now one of the sort of simple or first stage techniques that we'll go over for doing more complicated analysis of our images is K-means clustering. And has everyone heard of K-means before? Or raise your hand if you've heard of it before or used it before. Okay, so 3 or 4. Okay, so K-means is a very important technique to know. It comes, again, from sort of this statistical analysis or machine learning world. And it's one of the first kind of tools that you learn to use because it's fast, scalable, and it doesn't require any sort of a priori information. And so there's a lot of techniques where, if you learn a decision tree, it's a nice technique, but it can be complicated to set it up to learn correctly, and you have to understand a lot about your data. And what's nice about K-means is you can just throw data at it, and the only thing you have to give it is the number of groups you want to find, and then it finds those groups. And so if you really don't have any understanding of your data or don't know what to do with it, it's a very helpful technique for sort of separating it out. And so what the input to your system is really the feature vectors that you have. And so this is this intensity, distance, Sobel, Gaussian, whatever other information you might have. A distance metric, and the number of groups. And what you get as sort of an output from it is a classification of each feature vector to a group. And that so how this works is that you have sort of the feature vector that you input into your system. And in this case, we input X, Y, intensity, Sobel, Gaussian. And so we include the position information as well. The distance metric is then a Euclidean distance metric. And so that just takes sort of the magnitude of the difference between these vectors, which is a simple approach. It doesn't always make sense because you see in this case, the values of X and Y go from 1 to 14, and the values of intensity go from 0 to 1. And so what would this mean for this grouping? Or why would this distance metric not be a good distance metric? Or potentially be a bad distance metric? Yeah.
Because the effect of distance might be over-evaluated. Because the absolute value of distance difference between pixels is so much bigger than intensity difference.
Yeah. So the spatial weights are much, much higher than the normal weights. And so if you try to use a standard Euclidean distance without normalizing or doing something else with your data before, then it will basically just group it based on position. Because the position is so much higher weighted or so much higher in value than the other values in your image. And so, this is just a simple example, but being aware that these kind of things can happen is very important for knowing how to use this technique. Because if you apply it to an image and you have it sort of the position scaled as position or as pixels and everything else is scaled from 0 to 1, then it will be completely dominated by the spatial position and the intensity won't even play a role. You then give it sort of the number of groups that you want to find, and then what it does is it randomly, or there's a number of different approaches, but usually it takes 2 points in your image or 2 random points in your list of feature vectors as starting center points or seed center points, finds all of the points in your image based on this distance metric that are closest to point A or point 1, the different groups that you've defined. And then it assigns them to that group if they're closer to that than to every other point. And so group 1 are the ones that are closer to the center of this group than they are to group 2. And I think, so this goes through the algorithm in more detail. So you basically randomly create center points, which we call sort of the group centers. you assign each point in your list to a group based on the one that it's closest to, and then you recalculate the centers from the means of each group. And so this is then an iterative approach that you can run until it converges or until you're done running the analysis. And that sort of divides your space up well. And so when we look at sort of the vector spaces that we have, we can include intensity or color. You can also include orientation, shape, other spatial pieces of information. And if you look for n groups, you will almost always find n groups. And so choosing this n and this distance metric are very important. And so making sure that your data and the way the distances are being measured makes sense is really important for this technique to work very well. And so if we do sort of the K-means example on our image, where we take the image we have and we classify it into two groups, if we classify it just based on the feature vector that we talked about initially, where we have intensity, Sobel, and Gaussian, then we divide our image into sort of these two different rings. So we have this ring here, which is group 1, and this ring here, which is group 2. And so that's sort of the first version. And if you then look for 5 groups, it will find 5 groups where you have your rings showing up like this. And so the groups aren't necessarily meaningful, but what they provide is some better understanding or better visualization of your data. And so with this data set, it isn't helpful to have that, but with a lot of the different images we have, it can be useful to get sort of an idea of how the data might be divided or how you can start to analyze it better. You know, if we then include position into it, and so this is where we include position as we had in the original part, where it was between -10 and 10 or -20 and 20. We then see that it completely ignores the intensity of the image and it just divides it up into spatial regions. And so that's why it's important to have a weight or sort of a distance metric that doesn't cause X and Y, or the spatial position, to be much more strongly evaluated than intensity, Sobel and Gaussian, or the other features that you have. And so you have to make sure that all of your features are somehow comparable in the same space. And this is one of the things that you'll have the opportunity to play with in the exercises, is you can change the weighting for these feature vectors and see how that changes the output image that you get. You know, for some kinds of analysis, this might be what you want to have, where you simply have different regions separated, but probably because it's an image, you want intensity and Sobel and Gaussian to play more of a role. So yeah, this is where we can show if we take this image and then rescale X and Y by a factor of 10, this then gives us a value for X and Y that is between sort of -1 and 1, instead of being between -10 and 10. And then when we apply this technique, we get sort of a division of our image that represents space as well as intensity. And so the ring structures come out much better. And it's looking at those other pieces of information that are part of the image. We also see that it, because we have this Sobel feature in here, we have this red, which is showing us where the really strong edges occur that sort of gets separated from the image. And so how you choose these features and which ones you include in your analysis will strongly determine what kind of results you get out. And so it's a very helpful technique for visualizing, but it's very, can be very easily affected by what you put into it. So the sort of extension of K-means to the imaging space is called superpixels. And so superpixels are sort of an idea that have been around for, I think, at least 20 or 30 years, but they have more recently become quite a bit more popular. And what this is this is a clustering of your image space where you try to conserve connectivity. And so when we saw before, we sort of had this list of feature vectors that we processed and ran kind of assigned to different groups. And here they happen to be well connected. I mean, the purple and the yellow are well connected, but we see that the red isn't well connected at all. And so it's here, it's here, it's here, and none of these points are close to each other at all. And so what superpixels are sort of the extension of this, where we start to look at points that are sort of connected together, and this helps us then identify relevant features inside of an image. And so when we look at this, we can then do a superpixel analysis on it, where we can then divide this up into different regions to look at more carefully. We can then see sort of the different superpixels and where they're centered inside of the image, and that the centers are sort of distributed in intensity, or in spatial position, as well as in intensity. So it's taking into account both of these pieces of information, and that can make it much easier to then segment our image from the set of superpixels. And so you have this distribution of superpixels, and then you can say, okay, the superpixels that are very bright, I want to call sort of this clay or light phase, and the superpixels that are very dark sort of make up this mineral phase. And so you can use this as sort of a pre-processing step to summarize your data much better. And so when we talked about the feature vectors that we created, if we go back here, that we have sort of this intensity, this Sobel, and this Gaussian. And when you add a new feature to this, like another Gaussian value or another metric here, that this is based on a square neighborhood in your image. And this might not be the best representation of your image that you can have. So that if you look at just a square box around the pixels that you have, as we showed with these neighborhood things, that this accounts for sort of that part of the image, but it doesn't account for boundaries and other aspects very well. And so particularly when you're looking at things like texture, you know, the texture at this point is the same as the texture at this point. It's all white, or it's all sort of the same high intensity purple here. And you don't want it to be affected by the fact that there's an edge right next to it. And so what you can use superpixels for is that superpixels will then group this image together so that regions that are homogeneous fall together, and you can analyze the texture and other parameters inside of these regions much easier. Yeah, and so that gives us sort of a division of the image that lets us look at things like texture and add features to it in a much more compressed space that's more homogeneous within itself. We can also sort of drastically reduce the amount of data that we have. That if we take sort of 0.06% of the original data and plot it against the full data set, that we still get a very, very good representation of our image. And so it allows us to throw away a lot of the information that we don't need and look at just a small subset of information that's easier to handle and process. So the last part that we'll just briefly go over, because it probably isn't as relevant for you at this point, but could still be interesting to look into, is this idea of sort of this probabilistic model of segmentation. And this falls in, again, very well with sort of this idea of ROC curves and these other parameters that we get out, is instead of trying to segment an image clearly into two phases, that we assign the probability at each point in our image of it belonging to phase A or phase B, or if there's more phases, then more phases there. And that's where we then don't come up with a final segmentation. We simply come up with a probability distribution. And that we say, you know, the probability of a given pixel being in phase A, given its position and value, and that's kind of what we're trying to estimate, and then we can include other pieces of information to try to express that better. And so what this gives us is really just a mathematical way of representing how we perform our segmentation and how we can sort of understand it and model it better. And so here you have this, which is sort of what you're ultimately trying to estimate. You have this, which is the probability of it sort of belonging to phase A a priori. And so if your image is 50% made up of bone and 50% made up of air, then this P would sort of be 0.5 because that's what your assumption is about your image, knowing that it's going to be around 50-50. You then have this probability based on sort of the intensity in your image that it belongs to phase A. And so if this phase, or phase alpha, and so if this alpha phase is air, then you would expect if the intensity is low, that probability value is small. And if the intensity is high, if the absorption is high, then this value is going to be very low. And if the value is low, then this probability is going to be very high. So if you're looking at calcification density, you would expect the calcification density of air to be 0. And so you'd expect this probability to sort of be inversely correlated to that. You then have this final component, which is based on the neighbors that you have around your pixels. And so if you're surrounded by pixels that are likely to be air, then the likelihood that your air is increased. And so this gives us a way of representing that for the image without having to say that this point is definitely air and this point is definitely bone. And so it just provides a much simpler way of representing that so that we can then use this probability and add other pieces of information to it easily without having concrete processing steps defined. You can also then begin to combine this with other approaches like Markov random fields in order to come up with better estimates for what these terms are that are more or better matched to the imaging modality that you're using. And so if you really understand your camera or your X-ray measurements well, then you can start to derive these terms very concretely. The next thing we'll go over very quickly is this idea of contouring. And so this is where you have sort of your image, and this is and you've segmented it, and you're trying to find sort of the boundaries or what makes up the region that this image falls into. And so, if you have a sample like a brain, you might have lots of holes or liquid inside of the brain, and so you want to identify the entire boundary of this region so that you can find holes inside of it easily. Or with bone, when we looked at the bone sample we have, it's made up of bone and air, but air that's inside of bone is probably a vessel or a cell, and air that's outside of bone is meaningless. And so we need some way of classifying these regions well. In material science, this can be very helpful to identify sort of how a sample's changing with time. And so if you can define a contour around it, it gives you a starting point for analyzing stress and strain in this sample. And there's a number of different approaches that are available. And so one of the most useful approaches that you've probably come across before, at least in mathematics class, is this idea of a convex hole. And so this is where you take all of the points in a given space, and so typically we're dealing with slices and volumes here, and you generate the convex hole that fits around it. And so for a circle, the convex hole that fits around it perfectly is a circle. As you sort of get into more complex shapes, then you see that this convex hole is sort of the simplest shape that fits all of those points in it while maintaining this convexity. And so it gives you sort of boundaries, but that may or may not be accurate. And so if you're looking at a flower here, this is clearly not part of the flower, but it's part of the convex hole. And so it provides a first approximation for where those boundaries might be, but it's not the sort of end-all approach for calculating this. We see for bone samples that, if you have a cortical bone, which is then full of marrow, that making a convex hole gives you a fairly accurate, quick representation of where the bone is and where the sort of marrow is inside of the bone, which can be a typically fairly challenging problem. But if you're just looking at a sub-region of it, then you see that this all gets classified as being part of the bone or inside the bone sample, even though it's probably not. I mean, it's probably a completely separate region that we don't want to include. So that's where we have more advanced approaches, even though they sound simpler, like this rubber band approach, where you then take your image and you fit a curve around it. So you have a piecewise linear fit of a polar coordinate curve around the sample that you have. And if you use sort of 9 points, then you get a very poor approximation for what this boundary could be. And if you use a larger number of points, 36, 180, 200, 720, then you get a much more accurate representation for what this boundary could be. And we see here that that fits very well with this image, and that it counts these sort of inlets as part of the bone, and this region not. And so this would already be a much better approximation than something like a convex hole for the features that we consider to be relevant inside of the sample. So of course, part of it's about knowing what is relevant and what's interesting, and being able to separate that from the problem that you have. You can also apply more flexible constraints. And so rather than taking the maximum value, you can take sort of the upper 99%, and that sort of shrinks your boundary a little bit and makes it much less sensitive to sort of single outlier points. You can also take the mean value. So you could look at the mean value inside of it to sort of find a region that was always safely inside of your sample. And then there's sort of these guided approaches where, if you've used the magnetic lasso in Photoshop, that this is sort of a good example of a tool where you have this idea of active contours or snakes coming in, where you draw, but it's being actively assisted by image information to try to guess what features you're trying to identify in the image. And so it's sort of semi-automatic in the sense that you are guiding it, but it's using image information to make the exact decision about which pixels get included and which pixels are not included. And one of the exercises today, if you're interested, shows how this tool works in a program called Mavis Lab, so that you can actually segment a complicated 3D feature out of an image where it's not very clear. And this is where I think we do the cortex segmentation in the brain. Oh. Yeah. So of course there's a multiple of techniques that we'll cover in sort of later parts of this lecture, but this covers really the basics and the ideas that are important for doing a segmentation well. And so, we will, of course, there are much more advanced things that you can do, but they're built off of these ideas. And so really having this idea of the ROC curve that you're optimizing, having this idea of a feature vector and how you assemble feature vectors to improve your image are the basis for trying to do this well. Cool. Yeah, and so we'll leave off that for now. If you're interested, you can look at those slides on your own. And now, are there any questions on that? Okay. So yeah, we can then start on the exercises.